This video is about predicate logic. On this slide, we have a couple of mathematical statements that exemplify many mathematical statements. The first says all continuous functions on the closed interval a,b are Riemann integrable. And the second says there exists a continuous nowhere differentiable function. So you might recognize that both of these statements are from calculus, but that's not what I want you to notice at the moment about these statements. What I really want you to pay attention to in the first statement is the word all. So the first statement is a statement about every one of something. In this case, we're talking about every continuous function on a closed interval. The second statement has to do with the existence of something. So these two words, there exists, are important. That means we're looking for at least one of something. In this case, we're looking for at least one continuous nowhere differentiable function. So the first statement is what we call a universal statement because it has to do with all of something. And the second statement is what we call an existential statement because it asserts the existence of something. So it's our business in the next few slides to investigate the nature of statements such as these. To form universal and existential statements, we first need what are called predicates. So a predicate is something that is nearly a statement. In fact, a predicate is a declarative sentence with variables that becomes a statement when the variables are given specific values. Now, every predicate comes with a domain. So the domain of a predicate is just the collection of allowable values for the variables in the predicate. So here we have some examples. First, we have the predicate P of x, where we're saying the predicate is x is poisonous. Now, the domain of this predicate could be anything. It could be snakes, it could be spiders, it could be all kinds of things. But here we're going to declare the domain to be equal to plants. Now, every time we replace the variable with some specific member of the domain, we get an honest-to-goodness statement, which is either true or false. So, for example, if I were to look at P of, say, hemlock, which is a poisonous plant, by the way, then that would be a true statement. Whereas P of lettuce would be false because lettuce is not a poisonous plant. Okay, our second predicate is a similar sort of thing. So here we have A of x, and the predicate is Ava has eaten x. And here x could be all kinds of things. It could be meats, it could be fungus, it could be whatever. But here, again, we're going to declare the domain to be plants. And so if we looked at, say, A of lettuce, that's definitely a statement. It's the statement that Ava has eaten lettuce. And unless Ava is here to tell us whether this is true or false, we don't know right offhand whether it's true or false, but we do know it's a statement. Okay, now finally we have this predicate R of xy, which says x times y equals 1. So the thing to notice about this predicate is that it involves more than one variable, which is completely allowable. Again, we need to declare a domain, and here the domain is going to be non-zero rational numbers for both x and y. So again, when we plug in specific values for x and y, we get a statement. So maybe we take our 2, 1/3. So 2 and 1/3 are both non-zero rational numbers. And we want to know whether 2 times 1/3 is equal to 1, and in fact it is not, so that's a false statement. On the previous slide, we saw that we can convert a predicate to a statement by replacing the variable by a specific value. Another and very common way to convert a predicate to a statement is to use what's called a quantifier. So there are 2 quantifiers. One is the universal quantifier, and it is denoted by this upside down A, and it means for all. The other quantifier is called the existential quantifier, denoted by this backwards E, and it means there exists. So we can use these quantifiers, as I just mentioned, to convert predicates to statements. So if S of x is a predicate, we can form the following universal statement for all x, S of x, as follows. So that is the statement that S of x is true for all possible values of x in the domain. We also have what's called an existential statement. So there exists x, S of x, is the statement that S of x is true for at least one value of x in the domain. Here we get some practice with statements involving quantifiers. First, I want you to remember the predicates that we introduced a couple of slides ago. We have P of x, A of x, and R of xy. And below those, we see an entire list of statements involving quantifiers that we're going to translate to English. So the first one is an existential statement. It says, there exists x, P of x. So P of x is poisonous, and we're looking in the domain of plants, and the quantifier is existential. So this is saying that this is the statement that there exists at least one poisonous plant. Or maybe more succinctly, there are some poisonous plants. Okay, now the second statement is using the universal quantifier. It says for all x, ax. And if we go up and we look at what ax says, and we remember the meaning of the universal quantifier, this is saying that Ava has eaten all plants. Which I suspect is not a true statement. Okay, so now we're on to the third bullet, which is, again, an existential statement. So we're asserting that there is at least one x in the domain such that P of x and A of x is true. If we go and we look at what P of x and A of x say, maybe we conclude that this is the statement that Ava has eaten a poisonous plant. Okay, and now we're on to the fourth bullet, which again is universal quantifier. It says for all x, if the plant is poisonous, then Ava has eaten it. So there are a number of ways that we could write this down. In fact, we could write it down exactly as I just said it. You know, for all x, if the plant is poisonous, if a plant is poisonous, then Ava has eaten it. I mean, another way that we could write down something equivalent is we could say that Ava has eaten every poisonous plant. Okay, so that deals with the, that's the first 4 bullets. And so now we have just these 2 remaining. And what you might notice about these 2 is that they involve not just 1, but 2 of these quantifiers in the statement. So to address those, I'm going to go ahead and erase the results to these previous responses so that we'll have a little bit more room on the slide to deal with these last 2 bullet points. Okay. So the first statement, the first bullet there says, for all x, there exists y such that x times y equals 1. So let's just write that down. For all x, there exists a y such that x times y equals 1. And we have to remember that we're restricting ourselves to the domain of non-zero rational numbers when we say these things. All right, so before that, that's the translation of this 5th bullet point. And now, I haven't been asking you this for the other statements, but for this one, I want you to consider whether this is a true statement. Right? And I think if you think about it for a little bit, you will come to the conclusion that this is a true statement, because for all x, if someone drives up and hands you an x, what you should do for y is choose y to be 1 over x. And then x times y will be equal to 1. Right, so this is a true statement. And the value of y that we choose depends on x. Right, so for all x, there exists a y which could depend on x such that x times y equals 1. So hopefully we agree that this is a true statement. So now let's move down to the 6th bullet point. And the only way it differs from the 5th bullet point is that the order of the quantifiers is reversed. We have there exists a y such that for all x, so there is a y such that for all x, we have x times y equaling 1. So now, again, I'm going to ask you whether this is a true statement. So is there a specific y such that for every single value of x, we have x times y equaling 1? And the answer here is that this is a false statement, right? Because, if you pick some value of y, then surely there's some other value of x where x times y is not equal to 1. Right, so the point here, aside from translating these statements, is that the order of the quantifiers matters in how we interpret the statement. Right, in particular, in the fifth bullet point, we got a statement that's a true statement. In the sixth bullet point, the statement is false. So on the previous slide, we got some practice translating quantifier statements expressed in terms of symbols into plain English. On this slide, we're going to do the opposite. We're going to take some predicates and some sentences in English and translate them into symbolic logic. So we again have the same predicates that we have been dealing with over the last few slides, that is P, A, and R. And now we have this list of sentences to translate to symbols. So the first is, Ava has eaten some plants, which I take to mean that there exists a plant that Ava has eaten. And I guess then I would write that like this. All right, now we have Ava has never eaten a poisonous plant. Now there are a number of different ways that we might express this. So the never sort of indicates that we should be using a universal quantifier. So for all x in the domain of plants, we have the statement that if it's poisonous, then Ava has not eaten it. Now, there are other ways to express this. So, you might think about some other way to express this in terms of symbolic logic. All right, now on to the third bullet point. So there are some non-poisonous plants that Ava has never eaten. So the sum sort of indicates that we're going to be using the existential quantifier. So there exists some plants that are non-poisonous, so not P of X, that Ava has never eaten, so and Ava has never eaten them. And now finally, there are non-zero rational numbers, x and y, with x times y equaling 1. So here, there are, that sort of indicates an existential quantifiers. So there exists an x and there exists a y within the domain of non-zero rational numbers such that x times y equals 1. So that's the corresponding statement in symbols. So there are two common quantifier statements that appear in many mathematical theorems. The first one says, for all x, if p of x, then q of x. Now that can also be translated as all p of x's are q of x's, or every p of x is a q of x. The second common quantifier statement involves the existential quantifier. It says there exists an x such that p of x and q of x is true, and that translates to also to there is a p of x that is a q of x, or some p of x's are q of x's. So below I have a couple of examples, but first I want you to think about the very first slide of this video where I showed you two theorems from calculus. So the first theorem was every continuous function on the closed interval AB is Riemann integrable. So that theorem actually takes the form of this first bullet point where the domain is functions, and P of x would be the statement that a function is continuous on the closed interval AB, and Q of x is the statement that a function is Riemann integrable. Now, the second theorem that was on that very first slide of the video was that there exists a continuous nowhere differentiable function. So again, that's an existential statement. Our domain, again, is the collection of functions. And here, maybe P of x is the predicate that, that x is continuous, and Q of x says that x is not differentiable. So both of those very famous theorems from calculus take these common forms. So some maybe less interesting examples are given here below on this slide. One is all squares are rectangles, and another, and that exemplifies the universal quantifier statement here. And then the other one says some even integers are divisible by 4. And that takes the form of this, this existential statement. Sometimes we would like to negate statements involving quantifiers. Now, if we're left to our own devices using just the English language as a guide, even if we are careful thinkers, it can be difficult to negate some of those statements. However, as we'll see, if we are able to translate those statements into symbols, and if we use certain equivalence rules for negation, then we can accurately negate all kinds of statements involving quantifiers. So to begin, let's look at these two statements. So the first is all professors eat asparagus, and we're to negate that statement. So we want to create a statement that has the opposite truth value. And, you know, you might just be thinking along with me that the negated statement is that there is a professor. Who does not eat asparagus. And then this next one is, there is a green cow in Indiana. So that's a statement involving the existential quantifier. And you could negate it by saying there is not a green cow in Indiana. But why don't we negate it this way by saying that all cows in Indiana are not green. So one thing I want you to notice about the construction of these negations is that in the first statement, we have this universal quantifier, all. All professors eat asparagus. And to negate that, all we need to do is show the existence of one professor who does not eat asparagus. Whereas in the second statement there was a claim about the existence of something. There is at least one green cow in Indiana. And to negate that, we assert that all cows in Indiana are not green. So these negations are examples of the following equivalence rules for negation. So if you want to negate the statement for all x, p of x, then what you do is bring the negation inside and replace the universal quantifier with an existential quantifier. And similarly, if you want to negate a statement involving the existential quantifier, you can move the negation inside and replace the quantifier with a universal quantifier. Let's get some practice negating statements involving quantifiers. So we have here a couple of predicates. The first is x is prime, and the second is x divides evenly into y, where the domain in both of these predicates is the collection of integers greater than 1. So the first statement for us to negate is every integer greater than 1 is prime. So we're going to negate this using English, and then we're also going to use symbols. So in English, the negation should be probably something like there is an integer greater than 1. That is not prime. Now, it's not required, but I might ask you about the truth of these statements, right? So I have the statement in the bullet point, and then I have its negation below. And one of them is true, and it's this one here. Okay, now in terms of symbols, what I'm trying to do, the first bullet point statement is for all x, p of x. Okay, that's the symbolic translation of the statement in this bullet point. Now its negation remember that to negate a statement like this, we move the negation inside and replace the quantifier with the opposite quantifier. So, we replace the universal quantifier with the existential quantifier. And when you translate this back to English, you'll get exactly this statement here that we came up with initially. There is an integer greater than 1 that is not prime. Here we have the same predicates that we had on the previous slide, and we have another statement involving quantifiers that we would like to negate. So the first thing we're going to do is take this statement in the bullet point and translate it to symbols. So the statement is for every integer x larger than 1, there is an integer y larger than 1 that divides evenly into x. So for every integer x larger than 1, there is an integer y larger than 1 such that y divides evenly into x. So now our goal is to negate that statement. So if we use our equivalence, rules involving negation, the first step is to move the negation inside the universal quantifier. So we change the universal quantifier to an existential quantifier. And now we go a little bit further, where the goal ultimately is to bring the negative sign or the negation inside all of the quantifiers. So we apply this rule again, where we bring the negation inside and we change the quantifier. So this is our end product because we can't move the negation sign inside any further. Okay, now what does that say in English? It might be worth it for us to try to write down what this is saying. So if we just read from left to right, this is saying that there exists or there is an x. Maybe we should be careful where there is an integer, x, greater than 1. Such that for all integers y greater than 1, we have that y does not divide x, or does not divide evenly into x. All right, now it's possible that if we didn't make use of symbols and we were just relying on our own devices and using the English language to negate this statement, it's possible we could do it correctly, but it's also possible that we could make some mistake. And so this translation to symbols helps us avoid making mistakes of logic and helps us to negate statements involving quantifiers accurately. Okay, let's do one more example here where we negate a quantifier statement. We're going to use the same predicates that we've been using over the last couple of slides. And our statement says, if 2 divides evenly into x, then x is not prime. So our first goal is to take that statement and translate it to symbols. So 2 divides evenly into x should look like this. So if 2 divides evenly into x, then x is not prime. Now to make this a statement, we need to include a quantifier. And the quantifier that is implied but not actually stated in the English version is the universal quantifier for all x in the domain. If 2 divides evenly into x, then x is not prime. Okay, so now we want to negate this. And so let's go ahead and start that down that path. And the first step is to use one of these negation equivalence rules, which tells us that we bring the negation inside the quantifier and then switch the quantifier. And at this point, you might be tempted to stop because we have brought the negation within the quantifier. But it turns out that the statement that is inside or to the right of the quantifier can still be simplified. So to see how we can do that, remember we have this equivalence rule known as implication that tells us that if P then Q is equivalent to not P or Q. Okay, so if you have your list of equivalence rules handy, you might look at that. It's called implication. So we're going to apply that here. So if we apply implication to the thing which is within the square braces, we get not Q 2 comma X or not PX. Okay, so there we applied implication. Now we can apply De Morgan's laws. So we have this original negation here. We can also bring this negation out in front. And finally, we can use double negation, right? That double negation is the same as doing nothing. So now if we translate the negation into English, it says that there is an integer x greater than 1 that is prime and even, right? Prime and if 2 divides evenly into x, then that means that x is even.